Hi, welcome to the lecture 57 in this course Classical Mechanics 1. We were discussing last few lectures on small oscillations. So, this is the last topic in this course and this is also the last week of this course. So, small oscillation in last class we have seen that if a potential has certain minima, then around the minima the particle will have a simple harmonic oscillation, and we have explicitly seen that for one dimensional case, and then we have started for a general n degrees of freedom system how we can analyze that small oscillation of that system. So, for that we let me define that things we defined yesterday, that we consider a potential which is n generalized coordinate, function of n generalized coordinate, and we assume that where qi equal to q0i are the equilibrium position. Of the system. Okay. So, now what happened that we want to look at the behavior of the system around the equilibrium position. So, we need to expand the potential around this point and we will construct the Lagrangian for a general system. So, in this general system we will consider how we can study the small oscillation. Okay. So, last class we arrived that this potential can be expanded in a Taylor series around this equilibrium, and we obtain the result I will write here will be V of q0i at the equilibrium position plus sum over k del v del qk, and this has to be calculated qk equal to q0k and qk equal to q0k, but equilibrium position will have the minima of the system. So, we can have this term 0, and then we have this half del 2v del qi. So, sum over ij del qj, and this is calculated at qi 0 and qi minus qi 0 qj minus q 0 j 0 I. Okay. So, we argue that this expression if effectively without loss of any generality can be written as half sum over I and j v I j q I q j, where v I j is a symmetric matrix. V I j is symmetric matrix. You may recall that we consider this constant term to be 0 by choosing our zeros of the potential energy, and also we can choose our coordinate system to take the equilibrium position that to be in the origin. Okay. So, in that all this situation you can have you can write this. So, this will be our starting point in today's lecture, that the potential V, which is function of this generalized coordinate, is basically half sum over j k. Let me write del 2 V del q j del q k okay, this is the value of the Vij. So this is the value of Vij. Let me which is basically half j sum over jk for all degrees of freedom v jk qj qk. Okay, so this is the potential general system can be written in this. Okay, so this will be our equation 1. Now what will be the kinetic term? So for kinetic term, kinetic energy term in general is a function of quadratic in velocities, that we know. So we can write in form like this: m, there will be a mass like term which we generally for simple system write half m v square. So that similar to this potential, we can have a kind of general, this mass can function of the coordinates, and then let us write q dot j q k dot. So general kinetic energy term can be written in this form, where this mjk is in general function of coordinates. So let us try to expand this, because it is also function of coordinates. So let us expand this around the so expand this quantity around the equilibrium. Of course, in the latter case, we have considered the equilibrium at the origin, so 0, 0. So it will have the expression m jk at 0 I, that means at the equilibrium, plus the Taylor series expanded terms j k q j q j minus q 0 j and so on. So in the lowest order, we can only return to this term, because we know that kinetic energy term is quadratic in velocity. So in the lowest order we keep to this term, which is the independent of coordinates. Okay, so that we are considering. So lowest order non-zero term, which is quadratic in velocity, will correspond to this term. So now we write the Lagrangian. So Lagrangian for the general system. We are considering will be L equal to half sum over jk m jk qj dot qk dot, where this is independent of coordinates now, and the potential we can write half sum over v I j. So or jk, we are same summation, we write jk and qj qk. Okay, and in this to be consistent with my note, let us denote this as tij. Okay, so I just make a change of notation, tjk qj dot qk dot minus half sum over jk v jk qj qk. So this is our Lagrangian. Let us denote this as equation 2. Okay. Now we will see what will be the equation of motion for such system, but here I want to remind you that around that equilibrium position we are expand the kinetic energy and the potential energy term. So, what happened that this quantity and this quantity are independent of coordinates. Not only that, they are also symmetric in j and k. So, this Tjk is also same as Tkj and Vij is Vji. So, they both are symmetric matrix. So, now we have written a Lagrangian which can describe the system, a general system around the equilibrium position, and also remind you that we have considered the equilibrium point to be around to be the origin. Okay. So, equation of motion. So, if you calculate Euler-Lagrangian equation for this system for say Qj coordinate. So, you will get sum over j t j k q j double dot plus sum over j v j k q j equal to 0. So, this is straightforward. So, you differentiate with respect to q j dot, you will get this term and the dt of that, and from the potential term. So, this will be the equation of motion. So, let us denote this as equation 3. Okay. But to understand this Lagrangian, this matrices, Lagrangian in these matrices and this equation of motion, let us consider a simple system of 2 degrees of freedom. So, I will consider, and then to realize this how this equations looks like, that I will explain. So, suppose I consider a Lagrangian in 2 dimensions. So, x, y, say let x dot, y dot. So, this is my Lagrangian. So, example to understand, example. Okay. So, let us half m x dot square plus y dot square plus a x dot y dot minus half k x square plus y square minus b x y. Suppose this is a Lagrangian. In general Lagrangian we have taken cross term also. So, kinetic energy term has to be expressed in this way such that you can get your Tjk matrix. So, let us see, and also keep in mind that it is symmetric. So, Tjk matrix we can, it is 2 dimensional. So, we can construct as, so this is m term in the diagonal x dot and m term in the diagonal y dot, and this has to be in symmetric, but half factor is outside. So, it will be actually 2. So, if you take half common, okay, let me write in a separate space. Okay. So, what I can write that this term as half m x dot square plus y dot square plus 2 a x dot y dot. Okay. Okay. And then further we can write half m x dot plus y square y dot square plus a x dot y dot plus a y dot x dot, right, because I have to write this matrix in symmetric way. So, this is very important when you solve the problems, you will understand when we solve the problems. So, this will be the half. So, this m in the diagonal, because x dot square coefficient is m, y dot square coefficient is m. Similarly, x dot y dot coefficient is a, so it will be a here, and a in the y dot x dot. So this will be the structure of your kinetic energy matrix in this our formulation. And what about the potential energy matrix Vjk matrix in this particular example? Exactly in the same way I will write. So you take common this half, and then you will have k times x square plus y square, and minus if you take outside, because in the Lagrangian potential energy is minus. Okay. So this will be x square plus y square, plus I can write bxy plus byx exactly in the similar fashion. So again it will be k and k in the diagonal, because coefficient of x square and y square are k. Similarly, xy term has coefficient b and b, so this will be your matrix. Okay. If there is no cross terms, then this matrices will be diagonal. So you can understand. Now try to understand this equation of motion. So I obtain this equation of motion. So let us see this what is the meaning of this equation of motion. So let me clear some here. So I can explain things in a different ink. Okay. So you have now j has two values. So sum over j t j k and say q j plus sum over j v j k q j equal to 0. This is our equation. Now say j equal to 1, because now j equal to 1. So we will have sum over, no, we consider k equal to 1. So k equal to 1. So sum over j is 1 and 2, t j, k is 1, q j plus sum over j equal to 1 to 2, v j 1 q j equal to 0. So if we expand, equation of motion will be t 1 1 q 1 double dot, I forgot this dot, double dot, plus t 2 1 q 2 double dot, okay, plus now v, if I similarly expand, v 1 1 q 1 plus v 2 1 q 2 equal to 0. This will be one of the equation. So in terms of x and y, will be this equation? So t 1 1 is nothing but your m. So t 1 1 is m, q 1 is say x double dot, plus t 2 1, t 2 1 is a, q 2 is y double dot, plus v 1 1 is k, q 1 is x, plus v 2 1 is b, y equal to 0. So just to understand this matrix equation, I just simplify this. Now calculate this equation of motion directly from the Lagrangian. So directly from the Lagrangian, if you calculate this equation, then you will get for x variable, say, so you will get, let me use a different ink. So if you calculate this equation, it will get m x double dot from the first term, then x dot derivative, so it will a y double dot. Now the del L del x, so del L del x will come from here, so plus, there is a minus in the Lagrangian formula, minus in the Lagrangian, so plus k x, there is x term here, So, it will be B y equal to 0. So, the equation I am getting from the matrix relation, equation 3 is same exactly. So, it is written in terms of. So, I hope you have understand this. So, for the discussion of small oscillation for a general system, we have to understand, we have to in general solve the equation 3. We have to find solution of equation 3 that we are going to discuss now. Okay. So, let me write the equation 3 here again. So, it is T j k q j q j double dot sum over j plus sum over j v j k q j equal to 0. So, this is the equation 3. Okay. So, I have written again. And now, we know the motion is oscillatory. That is all we have our starting point, that we expect a oscillatory motion, simple harmonic motion for one dimensional system we have shown around the equilibrium. So, we can look for a solution of this system as q j t as a say some coefficient a j e to the power minus I omega t minus delta j. So, we can look for a solution of this. So, motion is oscillatory. So, look for, so let me write here, we expect motion. So, try the solution, try this general solution. And it is natural because equations are second order differential equation. So, we will have two constants, which is the amplitude and the phase. So, Aj is the amplitude of the system or amplitude of the oscillatory motion. So, Aj is amplitude and delta j is phase. And without any loss of generality, we can take this phase to be 0. Okay. So, for a solution anyhow. So, the solution, okay, omega I want to mention, omega is the frequency of oscillation. And it is real, because if it is complex, then energy will not be conserved for the system. Okay. So, omega is real, because if it is complex, then energy will not be conserved. So, now let us substitute this 4 in equation 3. That means, we have to calculate qj dot. Qj dot will be Aj minus I omega times e to the power minus I omega t minus delta j. They are constants. Okay. So, then double dot qj double dot will be Aj, and then again I omega square e to the power minus I omega t minus delta j. This is simple differentiation, and you will find this is nothing but minus omega square times qj. Okay. Because this Aj times this term, again I substitute by this, and minus I omega square is minus omega square. So, if we substitute this in the equation 3, you will get V. So, putting this, equation 3, you obtain V j k minus omega square T j k times Q times A j. How I get that omega square? Just a moment. So, if I differentiate, I'll get this. So, this will be Q j equal to 0. Okay. Okay. So, this you will a linear algebraic equation. So, we obtain linear algebraic equation as a solution for this, and we know that solution of this equation. So, let us denote this is equation 5. Solution of this equation will exist or before that, let me write equation 5 as V j k minus omega square T j k. Okay. So, solution of the equation 5 will exist if this is a known result. Determinant of this matrix will be 0, right. Coefficient, determinant of the coefficient matrix will be 0. So, that is the condition. So, you will have basically denote at equation 6. So, basically you have to solve this. So, this equation is called characteristic equation or secular equation, and this will give you the values. Solution will give you the values of the omega square, that values of the frequency of this oscillation. Okay. So, if you have a n dimensional system, so for a n dimensional system, you will get n such frequencies. Okay. So, you will find, so what we have discussed, we have in this lecture, let me summarize. We have discussed that a general n dimensional system, if we study that system near the equilibrium, then you will find that we will able to find n oscillation, n frequency of oscillation around the equilibrium position, which can be obtained from this equation 6, because equation 5 will have a solution. So, you will for all Qj, provided the coefficient determinant will be 0. Okay. So, demanding on that, you will find that this n frequencies of this system. Okay. So, in next class we will consider an explicit example and we will understand all this general formulation I derive in this class. Okay. So, this is for this lecture. So, in the next lecture we will consider the explicit example in a two-dimensional system, the well-known problem to you, and we will obtain these omegas, we will calculate these omegas explicitly. Okay. Bye for now.